What's up, guys? Welcome back. Let's move on to Narnia 2. Well, first thing you do, look at the source code, see what we're dealing with. Alright. Okay, so this is like, I think, probably the most classic format of one of these buffer overflow attacks that you're going to find. So this str copy function is well known to be like really unsafe. It doesn't check the length. So there's only 128 bytes reserved for buffer here, and anymore it's literally going to start overwriting some other stuff. And you know, there's no limit to this argument one that you can pass as many bytes as you want in. So let me demonstrate that. So one, and then what we're doing here is, if I do, let's just give it like 132 A's, right? Oops. Not Narnia 1. Get a segmentation fault. So what just happened? Actually, that's weird. I think actually, yeah. So the way function calls work at the machine level is every process has a stack. And every time you call a new function, the data from the old function is kind of saved onto the stack, and then the stack pointer is pushed down to make room for the data dealing with the new function. And one of the things that is pushed onto the stack is actually like the return address for the caller function. So that way, when it's done with the second function, it can just look at the stack, look at where it was before, and then kind of jump back to that address, that memory address. And what I did is I passed in so many A's that it actually, this is on the stack, right? And it went up, 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 and it actually, you know what? This will be better to demonstrate inside GDB. GDB is super useful for this stuff, guys. I don't really think you could do it without. Maybe you can. I'm not an expert, but yeah. So let's put a breakpoint after it does the copy. Okay, and run. And pass in the same input here. So there's 128 bytes, I think we said, right? Yeah, so if I do 132, let's see what happens. Actually, I should do a before and after. Yeah. So I'll show you the stack before we do the copy and after. So, yeah, so pass in our big string here. 132 A's. And let's see what that looks like. All right, so I can look at the ESP here. This register tells you where the top of the stack is. And, well, actually the bottom of the stack, because the stack grows down. So the way that works is when you want to create more room on the stack, you actually subtract from the stack pointer, so it grows down like this. That's not really important. But just so you know, if you want to look what's on the stack, you want to print the values going up. So from C0 up to 00. This is the earlier stuff on the stack, and this is the newer stuff on the stack. And then, so we got 128 things here, and then this right here, to me, this looks like our memory address. So we're looking at with that is if we look at the instructions there. Yeah. It's hard for me to demonstrate because, you know, this is like main itself. So somebody else called into main and then they put their address on the string. So when main returns, it's going to go back to here. I guess that's basically all you need to understand for right now. So then if I do a continue, now we look at the stack again. We can see everything got overridden with A's here. Oh, you know what? That's right. Okay. This is actually our return address, not this one. My bad. I think this might be a string. Yeah. A lot of times these 0804 addresses, these are like, this is where your like static compiled in data is stored in the process. And also any functions that you write yourself. So you can see like main, the code for main is stored at this area too. But F7 here, this is typically, from my experience, this is where the kind of the system code is at. So there's like a system function here that you know, Linux binaries have, and it calls into main. It's like the entry point. So this is probably the return address, and so when I continue here, we get a segmentation fault. I actually don't know why that seg faulted, because so if we restart the program, oops, no. Let's look at the stack before we do our copy, right? And so we have yes, I see what happened. So this is the actual return address, and what I did is when I copied my string in, it added the null byte at the end of the string here. So it slightly messed up the address, but it didn't completely overwrite it. And so basically what we know is that if we restart, we need to bump this up by 4 because there's actually another 4-byte word here before the return address. I'm pretty sure this is the old base pointer for the last function, which seems to be 0, and honestly I don't know why that is. I think that might be because the main is a special function, so the function before it didn't have a base pointer, perhaps. I don't know. It's not important, but this is the return address. So if we do A times 136 here, okay, you can see that it's gonna try to, it got overridden with all these A's. So it actually tried to jump to this address here, which is obviously just the bullshit address. So what you want to do now is put an address in there that is actually useful for us. So what I'm gonna do is I'm gonna put the same shellcode from last time in the buffer itself, and then I'm gonna give it the address to the buffer. Okay, so what's the address of the buffer? So I want to do 130. I want to do put the shellcode in. I know this code didn't work last time, but it's been working for me mostly, so I'm just gonna try it again. I'm going to put the shellcode in, right? So that's 23 bytes. So if we have 109 more bytes of padding. So then I'm going to do A times 109. And then I want to put the address of like, so it kind of goes back around to the beginning of the buffer, right? So put the address to the buffer here. We just got to figure out what that is, right? So right now I'm just going to put in these F's as a placeholder. Okay, we're going to restart the function, and then we're going to take a look. Let's see, what is our buffer address? Okay. Ooh, nope, that was not what it wanted. Print A, print that. Oh. Okay. So let's take a look. If we do this, yeah, so we're right here at the str copy. So if we look at the top two bytes, these are the arguments. The str copy, it takes 2 arguments, 2 buffers. So this D5, the stack pointer is D5, and this is D5. So this is probably the buffer on the stack itself, and this D8 is a little bit further up. So I think that's my argv. I can actually verify that. Yeah, so that's what I just passed in right here, stored here, and then this is just where it's gonna get copied to. This is our buffer. So now I'm gonna go in and replace FFFF D5C8. If everything looks right, we should get a shell. Yep. So we can see executing a new program /bin/dash. All right. Now I'm gonna get out of here and let's do it for real. So do this, and I actually don't think this is gonna work right off the bat. Yeah, because unfortunately, this stuff doesn't always work. The addresses are kind of changed from GDB to like the actual live environment. So what I like to do here is generate a core dump of the process itself outside of GDB so I can get the actual addresses there. Unfortunately, I'm pretty sure this system that I'm on is set up so you don't get the core dump files when you're running a set UID process for security reasons, but there should be an easy way around that. So I have this. You can't make files in your own home directory here, but you can create a temp directory. Oh, never mind. I'll just make a new one. So just use this make temp -d. So give me a. All right. So now what I'm gonna do is I'm gonna copy the binary into here. And also, okay, so we have to make sure that we keep the same length of the command. So I'm gonna have to pad it a little bit, and the reason we have to do that is because this string for the command is actually stored on the stack too, so it's going to affect the offset of where how far down the stack we are when we're creating the buffer. So I need to make sure I can see this one is 14 characters long, and so what I need here is I'm going to be running it like that, right? So I just need to map it. There we go. Okay. Oops. Like that, right? So I want it to be named this. All right, beautiful. And now just go back here, and we're gonna see, hopefully get us the seg fault again, and then we can take a look at the core dump file that's generated. See, now that it's not, since when I copied it, I lost the set UID flag, and that's why I think I can now get this file. So now I can actually open up that in GDB. Right, so XFFFF. Okay, so what I want to look at is, I'm just gonna look around a little bit, try to find where the buffer is here. All right, so it looks like these are where the A's are, but we wanna. I'm just gonna keep going back and back and back until I find it. Okay, so D5A8. Okay, yeah. So if we look at our shellcode here, it starts 31C05060A. I found it here. The address is D5A8. Okay, so get out, and I'm gonna. This looks like it's just off by a little bit, and then nope, look at that, we got a shell. But like I said, the set UID bit was unset when I copied it, so hopefully now this is gonna work with the actual. All right, looking good. And now we can see if I can actually run bash here. Nice. There we go. Oh. Narnia too. Maybe executing bash changed to what? Huh, that's okay. Whatever. I can't explain that, but it doesn't really matter. There's the password. Alright guys, I'll see you next time. Thanks.